Here we have the beautiful formula for population variance. We are taking the individual deviations, and we'll look at an example of this in just a moment. We're squaring those individual deviations. We're adding up all the squares, and we're taking an average, right? We just add a bunch of stuff up and divide by the number of data points. The average squared deviation from the population mean, that is the population variance. Now, let's take a look at an example together. This is real data on billionaires by country, and we're looking at billionaires per capita. We're going to give you a chance to get in and play around with this and make your own population variance and population standard deviation and all that good stuff. By the way, how do you do that? Well, we make the link available to you within the class, and you're going to go down to File, make a copy, and then you'll be off on your merry way and you can play around with this. So let's take a look more carefully. We're going to have a deviation column coming up at you and a squared deviation column coming up at you. And we have like the number of billionaires per 10,000. So Hong Kong is number one, at least in April of 2024, and that's 8.936 billionaires per 10,000. USA comes in at 2.42, for instance. Finland comes in at 1.256. You get the idea. Okay, well, what we're going to do first is we are going to take an average. We're going to say equals average. And Google Sheets just suggests the data C4 to C26. We're going to go with that. And we get, on average, for these 22 countries, we get 2.37 billionaires per 10,000. This brings up an interesting point. We are assuming for the purposes of this lesson, for this exercise, that we are interested in total billionaires for the top 22 countries in the year 2024, and we're assuming we are working with all the data. In other words, not just a sample, but we truly have the population of interest to us. Things get a little different if we're working with a sample, and we'll take a look at that in a future lesson coming up here. This column D is just to create a nice clean deviation so you can see where the deviations are coming from. So we have our actual data point and our average. Now, to calculate the average, what I put in is equals $C, $27. You may recall that those dollar signs fix the value right on this cell, like they don't float. And what happens is if I put that and then I drag down, it keeps referencing the same cell because of the dollar signs. It's an absolute reference. So now we have this column that's our average column, stays the same, right? Because that's the population mean for billionaires per capita across these nations in 2024. Now I'm going to create the individual deviations. And for the individual deviations, all I'm doing is taking the actual observation, in this case 8.936, and I am subtracting the population mean, mu, and I am going to autofill that down. It'll probably mess with my formatting a little bit and do some funky things down here. That's okay, we'll get over that. But one thing that's kind of interesting is what would happen if we summed up all of these deviations. It looks like some of them are positive and some of them are negative. You know, what happens? Hopefully you can guess. Because we are subtracting the mean from every data point, the mean just does its job so well, and we're going to find that every single time, no matter how much variation we have in our underlying data, and there's clearly variation here, right? These numbers are not all the same. But when we take all the individual deviations of the data from the population mean, we're going to get 0 every single time. And that's not really what we're after. And so we get around this problem of cancellation by squaring each of the deviations. A positive number squared is positive. A negative number squared is also positive. So this is a different way about going about the process. Pay attention closely here. What I'm going to do is I'm going to take the deviation and I'm going to put in this caret sign, which is an exponent, and I'm going to square it. And now it says, hey, do you want to autofill? And I say, sure. Now I get all the squared deviations just to see what's going on. 6 squared is 36, 7 squared is 49. We've got 6.56. That's 43.07, somewhere in the middle. Hopefully you get the sense that these are indeed squared deviations. That's the symbol up here, right? It's the symbol over here. So what does this formula tell us to do? Well, it says first take the squared deviations and then add them all together and divide by the number of independent observations. Well, let's just see, how many independent observations do we have? Looks like we have 22. So we'll put in 22 for our independent observations. And here we are going to sum, not average, but sum our squared deviations. And now it kind of just comes down to, how do we take an average? Well, we add a bunch of values together and then we divide by the number of independent values. So we're going to do 89.88, the sum of squared deviations from the mean, and then we are going to simply divide. And we come up with a population variance here of 4.09. I mean, really, we could do the same thing here. We would just come up with a big 0, because 0 divided by 22 is 0. This becomes our population variance. It's the average squared deviation from the mean. And I want to show you one last thing before we check out, is there's a much faster way to do all this, and it's in Google Sheets. If I just put in equals var.p, that p stands for population variance, and all I do is highlight all these values of interest to me, I get 4.09, which is the same 4.09 that came about from me doing things the long way. So we'll do a little bit of reformatting here just to show you. Sometimes when you're working through the stuff, you make a little bit of a mess, and that's all right. And we'll head on here and here, this is like the real nuts and bolts stuff of working. We're good. We have our population variance that we calculated by hand, as it were, or the long way. And then we also went in and just said equals var p and highlighted the values and saw that we came up with the same thing. And now it's your turn. We want you to calculate the population variance. We've given you a list of step-by-step instructions so that you can take it the long way and also the short way and see for yourself. There's a lot of value in trying things out on your own. It's all the same data, but instead of billionaires per capita or number of billionaires per 10,000, it's the raw number of billionaires estimated by Forbes in April of 2024. So 813 billionaires in the US, 406 in China, etc. Have at and see if you can calculate the population variance.